morning students. In the previous lecture we have two application of Gauss law. In this lecture we start from the third application of Gauss law. What is third application? The third application is electric field due to uniformly charged hollow sphere or maybe shell. Okay? For this, sigma be the surface charge density. Sigma be the surface charge density. So the charge is uniformly distributed over the sphere. Okay. The radius of hollow sphere is R, capital R. Okay. Now the field at any point may be inside or outside depend on R, that is the radius of surface, and must be radial as we can see from the diagram. Okay. Now in case of hollow sphere there are three cases. Once again there are three cases. One is outside, second on the surface, and third is inside the hollow sphere. Okay. First we take outside the sphere. So electric field outside the sphere. Okay. For this, consider a point P. Consider a point P outside the hollow sphere. Okay. To calculate electric field at point P, draw a Gaussian surface in the form of a sphere. This is represented by dotted lines. Okay. With radius R. With radius R. Okay. Passes through point P. Okay. Now, electric flux through an area element ds, a small area element, then d phi is equal to dot product of E into ds. Okay. As from the diagram, E and ds both are in same direction, so angle between them is 0. Then E ds cos 0. Cos 0 is 1. So d phi is equal to E into ds. Okay. Then total flux through Gaussian surface, that is sphere with radius r, small r. Then phi is equal to integration of d phi, that is E into ds, but E is constant, so E integration of ds. The surface area of sphere is 4 pi r square. Okay, so phi is equal to E into 4 pi r square. Okay, equation number 1. Then charge enclosed by Gaussian surface, and as you know that Gaussian surface is in the form of sphere, then Q is equal to sigma A, but charge is only bound to the radius capital R. Then in the place of A, area sigma into 4 pi capital R square. Equation number 2. Okay. Now according to Gauss law is saying that flux is equal to Q upon epsilon naught. Then put the value of phi and Q from equation 1 and 2. Then E into 4 pi r square equal to sigma into 4 pi capital R square upon epsilon naught. In next step, E is equal to sigma upon epsilon naught capital R square upon small r square. But as you know that sigma is equal to Q upon A, then Q upon 4 pi R square. Then we get E is equal to 1 upon 4 pi epsilon naught Q upon small r square. And from this we get electric field is inversely proportional to the radius of Gaussian surface. Once again, electric field is inversely proportional to the square of radius of Gaussian surface. Okay. In the second case, electric field at a point on the surface of hollow sphere. On the surface of hollow sphere. Okay. In this case, small r becomes capital R. Okay. Both the radius are equal. We know that E is equal to sigma upon epsilon naught capital R square upon small r square, as we have discussed in first case. Okay. Then put the value of small r. Then we get sigma upon epsilon naught capital R square upon capital R square. Then we get the value of electric field E is equal to sigma upon epsilon naught. Okay. But the value of sigma is Q upon 4 pi R square, because charge is bound to the radius capital R. Then we get electric field E is equal to 1 upon 4 pi epsilon naught Q upon R square. Okay. Now the third case is electric field at a point inside the sphere. Now we are taking the point inside the sphere. Dotted line represent Gaussian surface. Okay. So total flux through the Gaussian surface is phi is equal to E into 4 pi R square, as we have discussed in case first. Okay. Then charge enclosed by Gaussian surface. Now you can see from the diagram, Gaussian surface encloses no charge. Charge reside outside the Gaussian surface. Then charge is 0. Okay. According to Gauss law, phi is equal to Q upon epsilon naught. Then put the value of phi and Q from equation 1 and 2. Then we get E into 4 pi small r square equal to 0. And we get electric field is equal to 0 inside the sphere. Okay. In the third application of Gauss law, we have three cases. That is electric field inside the hollow sphere, electric field on the surface of hollow sphere, electric field outside the hollow sphere. Okay. So the variation of electric field with distance in case of hollow sphere is represented by this graph, as in first case or maybe in third case, electric field is equal to 0. So inside the hollow sphere, electric field is 0. This is represented by this portion, R less than capital R. For this portion, this is inside the hollow sphere. The electric field is 0. Okay. Electric field on the surface, that is E is equal to 1 upon 4 pi epsilon naught Q upon R square. It is the maximum value, and with this maximum value the graph is indicating at this point. This is the maximum value. Okay. Then in the third part, electric field outside the sphere, E is equal to 1 upon 4 pi epsilon naught Q upon R square, which represent electric field is inversely proportional to square of distance for outside the hollow sphere. This is represented by this portion. Then for R much larger than capital R, electric field decreases with the increase in distance. Okay, so this is outside variations. Okay, now in this way the chapter 1 complete, and we give the some hint of NCERT exercise. For question number 14, in question number 14, 3 charged particles are given to you. Then for hint for you is F is equal to ma. Okay, and also F is equal to small e capital E. This is derived from F is equal to QE. Okay, then Ma is equal to small e capital E. Then A is equal to small e capital E upon M. From second equation of motion, y is equal to ut plus half at square. Put the value of u is 0 and A is equal to small e capital E upon M. Then we get y is equal to 0 into t plus half small e capital E upon M into t square. Then from this we can see that most of quantities are constant. Then y is directly proportional to E upon M. In this way you can solve this problem, that for which particle E by M ratio is large. Okay, then question number 18. In question number 18, one square is given to you, so make the cube with the help of square. Okay, then the charge q is enclosed by the cube. Total electric flux through the cube, phi is equal to q upon epsilon naught, because charge q is enclosed by the cube. Then flux through the square, as the question says. Then square is the one face, because a cube has 6 faces and it is the square is the base of cube. So one face, flux through one face, that is phi is equal to 1 upon 6 q upon epsilon naught. In this way you can solve the NCERT exercise. Okay.